All right, section 2.7 is called implicit differentiation. So what I want to say is that we've actually done something called explicit differentiation already. We just didn't call it that. So explicit differentiation is taking a derivative where you have an equation of y in terms of x. So if it's not already in this form, and at least it can be put in the form where you have y on one side, y equals, and variables of x on the other side. And that's exactly what we've been doing so far. In fact, we've already started, the ones we've been working with already start out in the form y equals da-da-da-da, and then we take the derivative. Okay, so this is what we've been doing already. It's actually explicit differentiation. Implicit differentiation is taking the derivative of y in terms of x when you can't separate it to be y equals on one side and the variable x only on the other side. Or potentially it's just not convenient to do so. It might not be helpful to simplify that way. In order to use this method, we have to treat both x and y as though they are variables and then use all the derivative rules we've learned. Okay, can I go on to an example so you guys can see how it looks? Okay, so take a look at this equation. It doesn't say y equals, right? And you might think, well, we could just solve it for y, and that's true, we could. If we did, we'd end up having to eventually take a square root, though, because the y is currently squared. And when we took a square root, we get a plus or a minus. And we'd also have to have a quotient, because we would have to divide by the x squared that's currently being multiplied by the y squared. It would be very messy, let's say it that way. At the very least, it would be a very messy problem if we tried to solve it for y equals. This one we could actually do it. Sometimes we can't even do it, but it would be awfully yucky, okay? So we're going to do this implicitly on this problem, in part because that's the simplest way to do it. And so also in part because the directions told us to, but the direction told us to because it is the simplest way to do it. All right, so here's the deal. If you take a look right now at the x and the y, and you're treating them both as though they are both variables, then when you have x squared times y squared, what overall derivative rule are you going to be using? Product rule, because the x squared and the y squared are multiplied, right? So over here, the very first piece, I actually have a product rule. So the product rule says that I need to take the first piece and I need to write it down, right? I don't do anything with it. But then I take the derivative of y squared. So what would the derivative of y squared be? 2y. At least that's how it starts. And then we need to do dy dx. This is the part that becomes different than it was when you were doing it in explicit form. Think about it. Normally, when you have y equals and you have all of this, what's the derivative of y? Well, it's y prime or dy dx, right? I mean, that's what you do when you take the derivative of y. Well, when you take the derivative of y squared, you have to take the derivative of the fact that there's something squared, so pull the 2 down, rewrite the y, raise it to a power of 1. But then you also have to take the derivative of the inside, that is, what is the derivative of plain old y? Well, it's dy dx. So in a very real sense, right here, this is a chain rule, because y is itself a value that is a function of something else. So we've got to do the chain rule every time we see the y. Now, the other piece that we're going to do is we're going to take the derivative of the x squared. Now, that is just 2x, and you might think, well, why don't I have something dy dx like beside it? Well, because what's the derivative of x? Plain old x. 1, right? The derivative of x is 1. So if you treated this like, quote unquote, it was a chain rule, that's okay. It just doesn't give us any information that's particularly useful. I mean, it doesn't give us anything new that it didn't already have. So if you want to see the 1 written there, you can. I tend to not write that piece of it. And then I need the original of the second piece, so then it would be y squared. All right, now I have plus something. What's the derivative of 37? That's 0. So if you want to write plus 0, you can. Otherwise, you can write equals. And then I need the derivative of 4x, which would be 4. Now, this is sort of like if we were doing a gateway or a basic skills quiz like you guys did on Monday. This is where you would stop. But this actually wants us to find the derivative of y prime, or find the derivative of y prime x. What does that mean? Well, it means that at the very end, it should say y prime x equals, or in this case, we've used dy dx. It's easier to use dy dx because if you use y prime, the prime starts to look like a 1. That's why I'm not using it in this particular one. Your book tends to use the y prime on this particular notation, just so you're aware. But this is the piece that I want to solve for. I need to solve for this, which simply means I want to have it on a side all by itself. So right now, everything that's not dy dx needs to move somewhere else. What's the first thing that would move? 2xy squared. This piece right here needs to move first, and it can move with subtraction, right, Tristan? Okay. So right now I've got x squared 2y, and you can put the 2 in front if you'd like, dy dx equals, and now I have 4 minus 2xy squared. Does that look okay? Now what? Divide by x squared 2y, all of it, right, Edgar? So we'll divide both sides by everything that's not dy dx, so x squared 2y. And if there's anything that's reducible, right, anything that factors out of all of it, we can do that. Is there anything that simplifies from that expression? The 2, exactly. So this 2 and this 2 and this 4 can all be divided by 2. So this gives me 2, 1, and 1. So I end up having 2 minus xy squared divided by x squared y. Now, you might look at that and say, yeah, but I still have a y on the right-hand side, and the answer is yes, you do. There's not anything we can really do to fix that because we didn't have the original equation in y equals form, and we never solved for y equals on purpose because it was going to be awfully messy. So this is as simple as the answer is going to get for what we're looking at. Any questions on that one? Okay, let's try another one then. On this one, this is actually one where it wouldn't even be possible to solve for y, given the methods of algebra and so forth that you know so far. You couldn't even do it if you wanted to. However, you could, if you wanted to, go ahead and get that y out of the denominator and move it to the other side. So you could change this so it's not really written as though it were a quotient on the left. You could do that if you wanted to, but you're not going to be able to solve it for y equals any which way you do it. I'm going to leave it just like it is, just so you can see that that won't affect the answer at all either.
So anytime we have a y squared, does that mean we're going to solve it implicitly?
Yeah, the directions are going to be pretty explicit themselves about how to do it. Yeah, anytime you're seeing, basically, it's not really even the y squared, it's the fact that you're seeing it not written as y equals to start with. That's actually kind of your cue. So, and I think I have an example later on, let me see, where you could solve it if you wanted to for y. It's just not particularly helpful. Yeah, I've got one at the very end that we could solve it for y, but the directions actually tell us to do it explicitly. All right, so taking a look, we're going to go with it just like it is. That is, we're going to do the derivative on the left side as a product, or as a quotient rule. So what does the quotient rule say? Somebody walk me through what we should have. What do we do when we do a quotient rule? The denominator, right? We start with the denominator, which is just y. And then times what? Derivative of the top. So what is the derivative of x plus 3? That's just 1. And then the sign's going to be a negative, a subtraction sign. And then I need the derivative of the top. And I didn't say that right. The derivative of the bottom. So what's the derivative of the bottom? dy dx, exactly. Or y prime if you want to write that. Times what? Times the top, which would be the x plus 3. And this would be all over what? Y squared. I'm just following how I did it in my notes. I think it would have been nicer for us to actually multiply the other one to start with, but that's okay. All right, how about the right-hand side? What's the derivative of 4x? 4. And what's the derivative of y squared? Good, 2y dy dx. Nice. All right, so at this point I am going to go ahead and multiply by the y squared to the other side. My goal is to solve for dy dx. The problem is that I have 2 dy dx's, don't I? So if I want to solve for them, I'm going to have to get them onto the same side eventually. Otherwise, I don't stand a chance because they are separated on different sides of the equation right now. So I need to first get this denominator to sort of not be affecting the problem. So I'm going to multiply both sides by y squared. So on the left-hand side, of course, that cancels with the denominator, which is why we did it. And then I'm left with y minus, and I'm going to write these out. I've got x dy dx, and then I have minus 3 dy dx. So I actually have how many dy dx's? 3 of them, right? All right, now on the right-hand side, I'm going to distribute the y squared through. So I have 4y squared plus 2y cubed dy dx. Is everybody okay to that point? Okay, good. So in order to get the dy dx's on the same side, I just need to add or subtract something to move them around. Now, it would be kind of nice to move this piece because there's already 2 on the other side. So we could do that. But in some respects, it'd also be nice to move these 2 pieces because if I moved them, they would become positive. So I'm going to err on the side of I like things to be positive so I don't have to worry with negatives later. So that's how I'm going to approach this. If you do it the other direction, it'll still work without any problem. So I'm going to add the x dy dx and 3 dy dx to both sides. Now, at the same time, notice I don't really want the piece that doesn't have the dy dx where it is either. I'd like to move it too. So the 4y squared that's currently on the side that's going to have all my dy dx's, I'm going to move that at the same time. So I'm going to move this with minus 4y squared on the right and on the left. So we've done a massive subtraction addition thing. So these add to 0. And I'm left with y minus 4y squared. On the right-hand side, these add to 0. And then I'm left with 2y cubed dy dx plus x dy dx plus 3 dy dx. Now we're about to do some fancy algebra. Does anybody remember what you do next when you're trying to solve for something and it's in multiple terms? It feels a little bit like a trick. It's really not, but it feels like it. Well, you could if they had the same variable quantities, and they don't, though. So like one of them is y cubed, one of them is x, and one's 3.
What are we trying to do?
We're trying to get there to say just one dy dx. Right now I have dy dx, 3 of them there, and I just want one of them in a written form. You can factor it out. Exactly. So it feels a little bit like you're doing something tricky. You're really not, but it feels like it. So this is dy dx. And it factors out of all the terms. That's why we wanted all of the terms on the same side and nothing else there. So when I factor it out, I'm left with the 2y cubed plus x plus 3. And on the left, I still have the y minus 4y squared. Any idea what we might do next? Well, we could, but that doesn't help us. Our goal, remember, is to solve for dy dx. Yeah. So the part that we just factored out to put in the parentheses, we can divide that to the other side. So this 2y cubed plus x plus 3 can be divided on both sides. Or you can divide by it on both sides. And that actually solves dy dx. Solves for dy dx. And this one, when we get to the end here, notice there is nothing in all 5 of those terms that's common to anything. So there isn't any simplifying that I have a chance to do on that one. I really am simply done. So I found out here then that dy dx is actually equal to y minus 4y squared over 2y cubed plus x plus 3. Again, I still have y's on the right-hand side. That's not ideal, but that's the best we can do with the situation we're given. All right, now we actually are going to do one with trig next. So this one, also a good example. We could solve this for x, but in order to do that, we would have to employ arc sine. And you don't know derivatives for arc sine at this point, so that wouldn't be helpful. You couldn't finish the problem from there, so that's not what we want to do. However, we do have implicit differentiation we can use, and you'll notice that this x times y, which is a product, is inside of a sine function. So when you have an inside function, what is the overall rule that you're going to have to use? The chain rule. So we have a chain rule here. All right, so the chain rule says I need to take the derivative of the outside. So what is the derivative of sine? Cosine. Now what do I do? Yeah, I just rewrite the xy. Don't manipulate it at all. Just rewrite it. And I am going to keep using the parentheses just to remind ourselves that that is the whole inside. Next, I need to take the derivative of the inside, which I already let on just a moment ago, is a chain rule. I mean, is a product rule. X times y. So what are we going to do the derivative of x times y with the product rule? What will it look like? X dy dx. Good. So that we rewrite the first piece, and then we take the derivative of y, which is dy dx, plus y, because I have the derivative of x is 1, and then I rewrite the other piece, which is y, or in the reverse order of that's fine. So I have 1 times y. And all of this equals what? 2x. Very good. So don't get so caught up with the implicit part that the other part you just forget about it. It needs to be there too. All right, now the nice thing with what we're looking at is that we only have one dy dx here, right? I mean, that's actually fairly friendly. There's a couple of different ways we could do this. One option is that we could distribute the cosine xy through. The other option is we could flat out divide the cosine xy to the other side and move it instead of even distributing it. So what would you guys like to do, distribute or divide? Divide. Okay, so if we divide, the answer will look slightly different either way. It won't be different answers. It'll just look at it like a different form, just so that you're aware. So here's my cosine xy. So now I've actually got x dy dx plus y equals 2x over cosine xy. So now what would we do? Subtract a y. All right, so I'm going to have x dy dx equals 2x over cosine xy minus y. You could get a common denominator with that if you felt the need to do so or were manipulating it for some reason, but it doesn't really make anything any simpler to have a common denominator there, so we're going to just kind of leave it. What would I do as my last step? Yeah, we would divide by x. I'm going to write it a little differently simply because dividing by x is going to look kind of funny. For instance, if I do this, I'm going to end up with a fraction inside of a fraction. That's not especially nice. So I'm going to write it as though I'm multiplying by the reciprocal to every term. Is that okay with everyone? Just a little bit different way of displaying it algebraically. So the 1 over x times x, those would be reducing to the value 1. So I'm left with dy dx on the left. And then on the right, I have 2x over x cosine xy minus y over x. And this is a perfectly fine way for you to write this. You might see a problem like this written in the back of the book with a common denominator, so it might look something like this, 2x minus y cosine xy over x cosine xy. If you got a common denominator, that's what it would be. So that's fine if that's what they write in the back of the book. I'm fine if you leave it like this, though, as well. If you had distributed it through instead of divided it to the other side, it would automatically would have gotten a common denominator for you. So, is that one okay? All right. Take a look at this direction. It says to find and an equation of a tangent line at the given point. There in your problems, there's some of your problems that have an additional part to this that say something about if you have a CAS that will graph implicit curves, sketch and graph the tangent line. A CAS stands for Computer Algebra System, so they're the calculators like the TI-89 that Edgar has up here. I don't care if you have a CAS or if you're using a computer software system, you don't need to sketch these, okay? So I'm not going to ask that you sketch the implicit curve part. So if you see any directions that say sketch the implicit curve, you can ignore those pieces of directions. All right, but finding an equation of tangent line, that's something we've done quite a few times, isn't it? What's different about that direction than what we've been doing right now?
You have to solve for x and y eventually.
Yeah, you actually do. And you have to use the point slope of a form of a line, right? So y minus y1 equals m times x minus x1. Now, the beauty of the way your book approaches this is that when they ask you to find a tangent line and it's in implicit form, they actually give you x1 and y1. You don't have to find it. That's new, right? Before they would just give you at x equals 3 and you actually had to find the y value. So they're actually giving you those pieces of information. So y1 is pi thirds. And x1 is 2. So the only thing I really need to find is m. How do I find m? You take the derivative, exactly. So this derivative is another implicit rule. I have on the left-hand side some trig. I've got x times the cosine of y, so that is a product rule, right? And the y, again, is inside of the cosine function, so that's a chain rule. Yeah. And again, this is an example of one that if we tried to solve it for y, we'd have an arc cosine involved, and we don't have a derivative rule for that as of yet. Okay? So implicit's the only way we could do this problem. So overall, though, like we said, there is a product rule here. I have x times the cosine of y. So product rule says, what do I do first? Write the x. Fabulous. Next. Yeah, the derivative of cosine. So what's the derivative of cosine? Negative sign. I'm going to put the negative in front of the x so that I don't have to use parentheses because I don't want us to think it's minus a sign or anything like that. So I'm going to put the negative there. And what do I do after I'm writing down actually at sign? I put y. I don't change the inside function. Now what? Oh, good. We need the derivative of the inside. Amberly's right. I need dy dx here. All right. That is half of the product rule. Okay, it's the first piece rewritten. It's the derivative of the second one. Now what? Derivative of the first. So what's the derivative of x? 1. And then what? And then I write cosine of y. And all of this is supposed to equal what? 0, because the derivative of 1 on the right-hand side is 0. Don't get so carried away, you just rewrite the constants. You need to take their derivative as well. Now here's the cool thing. We don't really need to solve for dy dx in this general form. I mean, we need to solve for it eventually, but we need to solve for it at a specific location and time. That is, we need to solve for it when x is equal to 2 and when y is equal to pi thirds. So if you want, you can actually plug those values in right now without solving for dy dx in general, because that's not really what you need to do in this particular problem. If you solve for dy dx, that's fine. It won't hurt anything, but you probably have gone through a little bit more work than you really needed to. So I'm going to evaluate this at the point x equal to 2. So I've got negative 2 sine. I have a y value equal to pi over 3. dy dx is what I'm looking for, so that's still a variable in my problem. Plus, and then I have the cosine of the y value pi over 3 equals to 0. All right, so time to put on your thinking caps for trig. Remember all that good unit circle stuff that you did once upon a time, maybe recent, maybe not. And you need to figure out what is the sine value of pi thirds and what is the cosine value of pi thirds. So we'll start with sine. What's sine value of of pi thirds? That one's √3 over 2. Then we've got dy dx. The cosine value is, that's the 1/2. Yeah, the cosine value is 1/2. Now, at this point, everything here is numbers except for the dy dx. Now, you may not like the numbers that are there. There are radicals, but they are numbers. I don't have any more x's in the problem, okay? X's or y's. So the first piece can simplify this 2 and this -2, right? So I actually have negative square root of 3 dy dx. And I'm going to go ahead and move the 1/2 to the other side. That's negative 1/2. Right? What do I do next? Divide by the negative square root of 3, which is the same as multiplying by 1 over the negative square root of 3, since I've got a fraction on the right. All right, well, the two negatives are going to become positive, right? So I have dy dx on the left. I end up with 1 over 2 square root 3, which has sort of a problem. What's the problem? Yeah, I actually have something irrational in the denominator. So we had a discussion about a week ago about when we have radicals, when we simplify, when we don't, and so forth. And we talked about the fact that if there's variables under the radical, you don't have to do it. But when we have a number and you know it's not rational, that's when you simplify. So how do I make this irrational number rational? Right, on top and bottom, right, Edgar? All right, so I'm going to multiply the numerator and denominator by radical 3. Which is going to give me radical 3 over what? 6. So this right here is my slope. So this is radical 3 over 6. So what a fun problem. One piece of it's a whole number, 2. One piece has a pi in it, and one piece has a radical in it. My goodness. All right, so this is y minus pi thirds equals square root 3 over 6 times x minus 2. And we're going to simplify solve this for y equals. So, we'll distribute, right? So I have y minus pi thirds equals the square root of 3 over 6 times x. What happens when I multiply square root of 3 over 6 times 2? I have square root of 3 over 3. Right? Because that gives me 2 over 6, which is 1/3. Okay, great. And then we can add the pi thirds to the other side. Unfortunately, you can't really simplify that because they both don't have a radical and they both don't have a pi in them. But we can write this as square root 3 over 6x. You could combine, they do have the same denominator, so this would be plus pi minus radical 3. That'd be one way to do it, over 3. If you don't want to combine those into a single fraction, that's perfectly okay as well. It's really not a big deal. If you, in other words, if you left this piece right here as negative radical 3 over 3 plus pi over 3, and the first part written in as it was, that would be okay too. I think your back of your book does this first one, if I remember right from when I've seen it before. Okay, any questions on that one? It's kind of messy, but it wasn't undoable. All right, slightly different question. We have not seen a question like this before. This question asks us to find locations of certain kinds of tangent lines. So let's talk about what these actually mean. It says we're going to find the location for horizontal tangent lines and vertical tangent lines. So think with me, horizontal tangent line, what does it look like? Can you just put your arms in the air and show me what it looks like? Yeah, it looks like this, right? It's the flat line, right, like the floor or the ground would be. It's a line like the x-axis. What can you tell me about the slope on a horizontal line? It's 0. So right here, when we're talking about a horizontal line, we're talking a place where the slope equals 0. Now, in calculus, slope is the same as the derivative. So instead of writing m equals 0, I'm going to write what we really want is we want to find out where dy dx equals to 0. That's going to give me a horizontal tangent line, dy dx equaling 0. Now how about vertical? Hands in the air, arms in the air. What does a vertical line look like? Yeah. Okay, good. So it's going to be like the y-axis, right? Straight up and down. So think about the slope. What is the slope on a vertical line? Undefined. How do we get things that are undefined? Yeah, so this dy dx, or the slope, it needs to be undefined or does not exist. And in essence, we want something where a denominator is going to be equal to 0. So as we start working through this problem, be thinking about this. Eventually, I'm going to have a dy dx, and it's going to have a denominator. And wherever that denominator is equal to 0, that's the location we're talking about. Now, if it does have a numerator and denominator, which it will, and I want the whole thing to be equal to 0, what's that going to mean in terms of my function? Yeah, it's going to boil down to actually being that the numerator equals to 0. And I'll show you what I mean when we get there so you can make sure you're seeing that happen. But this will boil down to finding where a numerator and a denominator equal to 0. Wow, after all the complicated ones, this one is not so complicated, okay? So what is the derivative of x squared? 2x, nice. How about the derivative of y squared? Good, 2y dy dx. The derivative of 3y? Yeah, I'm going to have a negative in 3 dy dx. Good. And then on the right-hand side? 0. Excellent. Okay, now we've encountered this before, that is having multiple dy dx's. What did we do? Eventually, but before we factored, what did we do? Yeah, we need to move the 2x because it doesn't have a dy dx in it. So first thing is to move the 2x to the other side. So I've got 2y dy dx minus 3 dy dx equals negative 2x. And then Tristan hit the nail on the head, and a couple of you were echoing it as well. I need to factor this, right? So this is dy dx. And then I have 2y minus 3 equals negative 2x. Now what?
Divide.
Excellent. Divide by the 2y minus 3. So on the left-hand side, the purpose of that being that those two divide to 1, leaving me with dy dx. On the right-hand side, I have the negative 2x over 2y minus 3. So the two questions I was supposed to answer were about horizontal and vertical tangent lines. So my horizontal tangent line is when the entire dy dx is equal to 0. Well, the way that a fraction equals 0 is if the top does. If the top is equal to 0, the whole fraction is 0. All right? So I'm going to have a horizontal tangent line when my numerator is equal to 0. I have space? I do. Good. So my numerator is equal to 0 means that I have the negative 2x equal to 0, which means x is what? 0. Now, this is actually a location. X is equal to 0 in a lot of places on a graph. How do I find the specific location that this is referring to? We'll get to the vertical tangent line in a moment. We aren't there yet.
You can plug it into the original.
Right. And why is that going to help us, Amberly? What will that find for us? Y is, right? So what we're going to do is exactly what Amberly said. This equation right here gave us values for x and y as they are related to one another. If I'm looking for a location in the xy plane, right, it doesn't tell you to say very much to say I live on Kickapoo. Kickapoo's a long street. You might be looking for quite a while if all I say is Kickapoo. It's a problem here. X equals 0. Well, x equals 0 in a lot of places, right? The entire y-axis is x equals 0. Where? Where on the y-axis? Well, we need to find the other coordinate. So I can take this equation, x squared plus y squared minus 3y equals 4, and I can plug in x equals 0 to find out the y value that this is referring to. So if x is equal to 0, then I end up with y squared minus 3y equals 4. Then what do I do? Can't factor out a y. I mean, we can, it just doesn't give us an answer. What do you have to do to solve this equation?
Find the y.
We need to find the y. The reason that factoring out a y won't work is because what you were going to tell me next that you needed to do is to set things equal to the 4 on the other side. And that's not a process that works with 4 on the other side.
Would you use the quadratic equation?
You could use the quadratic formula. I think this one will simplify without that and be easier. We need to move the 4 to the other side. So this is y squared minus 3y minus 4. And even if we wanted to use the quadratic formula like you suggested, that's what we would do here too, right? We'd still have to move this to the other side. I think this one factors. Does it? Y minus y plus. Minus 4 plus 1. Does that give me the pieces in the right places? Remember our algebra enough to make sure that works? Okay, so this gave us y equals what? 4, and y equals -1, which means we have horizontal tangent lines at x equals 0, y equal 4, and x equals 0, y equal -1. So there's actually 2 horizontal tangent lines. Now, I'm going to give you a visual in just a moment about this graph to tell you why that makes sense, but for now, understand that that is what we've got here. We're in good shape. I'll move this up here. All right, the other thing we're supposed to find was vertical tangent lines. Coming back over here. Vertical tangent lines, we established a moment ago, mean that we need our slope to be, does not exist, or to be undefined. That means we need the denominator to be equal to 0. So I do have, in fact, a denominator of 2y minus 3, right? So my denominator of 2y minus 3 can be set equal to 0, and then what? Y equals 3 halves. I have one answer now for y. Y equals 3 halves. Now what? Exactly. Very good. So I'm going to plug in the 3 halves into the original equation. So this is going to be 3 halves squared plus y squared. I'm sorry, I put it in the wrong place. I put it in for x. My apologies. Let's try that again. X squared plus 3 halves squared minus 3 times 3 halves equals 4. This one's actually easier to solve for x because there's only one x in it, right? It's just flat out x squared. You can turn this into decimals if you feel more comfortable working with them. You can leave it in fractions as well. So this is x squared plus, so this would actually be 9 over 4 plus actually 9 over 2 equals to 4. If I get a common denominator here, then I would have 18 over 4. And did I do something wrong? Ah, thank you. That one right there. Thanks. All right, so I have 9 over 4 minus 18 over 4, which would be negative 9 over 4 then, right? Equals 4. Is everybody okay with that? I didn't actually show the 18 over 4 step, but that second fraction is actually 18 over 4 when I got a common denominator. I can add the 9 over 4 to the right. And I can also change this 4 to have a common denominator of 16 over 4. So now I have x squared on the left. What is 16 over 4 plus 9 over 4? 25 over 4, which is very friendly. Tristan's grinning at me. Because why? Yeah, the square root of it's actually a very friendly value. This is x equals what? Just 5 halves? Ah, plus or minus. We need that. So I have 2 points I found, right? I found 5 halves, and then the y equals 3 halves. Was it positive? Yeah. And I have negative 5 halves, and y is 3 halves. So these are the locations of my vertical tangent lines. Any guess as to what this picture would look like if you could graph it on a calculator? It's going to have 2 vertical tangent lines, 2 horizontal tangent lines. It's a circle. It is a circle, and in fact, if you remember a little bit about equations of circles, if you look back up at this, you might recognize that fact. This is simply a circle. Think about it. If you had a circle, will it have 2 locations where it has a horizontal tangent line? Absolutely will. 2 locations where it has a vertical tangent line? Absolutely will. All right, we have one more example. Second derivative. This is actually an example where we could solve this for y equals if we really wanted to do that to this problem because there is only one y in the one location. We're going to do this implicitly, but that would actually be something that we could potentially go through and do in this particular one. All right, finding the second derivative, double prime. What is the derivative of x to the 2/3? Good, 2/3 x to the negative 1/3. Now I need the derivative of y to the 2/3. It's going to start out looking the same, right? 2/3 y to the negative 1/3. But then what? dy dx equals 0. So we need to solve this now for dy dx. Okay, this is just like what we've done before, different function, but this is still the same process. So solving this for dy dx means the first thing I'm going to do is to move the 2/3 x to the negative 1/3 to the other side. Agreed? Okay. So I'm going to end up having 2/3 y to the negative 1/3 dy dx equals negative 2/3 x to the negative 1/3. Now what? Divide by the 2/3 y to the negative 1/3. What beautiful thing happens? I get the dy dx myself. What about on the left hand or the right hand side? The 2/3 cancel, don't they? So I actually have negative x to the negative 1/3 over y to the 1/3, negative 1/3, sorry. Now, we can go from here if you want to, but we could also change this so we don't have negative exponents. And I'm kind of a fan of doing that, so that's the route I'm going to go. If you don't want to change it, that's fine. You can do the problem differently. You'll get the same answer in the end. But I'm going to write this as y to the 1/3 over x to the 1/3. That's a property of exponents that you can switch the location between numerator and denominator when we have a quotient like this. Now, I'm supposed to be finding the second derivative, and this is just the first derivative, yes? So now I have to do it again. So the nice thing is that the second derivative itself is already written as dy dx here, so when I find the second derivative, it's already going to be solved for dy dx to the second, basically, whatever. Now, the notation for doing that, just so you know, you can write y double prime if you'd like. It's d2y dx2, looks like that, if you use this notation. And then we have what rule on the right? Quotient rule. So let me run through it with you quickly since we're running out of time. We've got the denominator times the derivative of the numerator, which would be negative 1/3 y to the negative 2/3, minus the numerator, which is a negative y to the 1/3, times the derivative of the denominator. Oh, I left something out. That's what happens when you start going too fast. There's a dy dx right there. Minus the numerator, which is y to the 1/3, times the derivative of the denominator, which is 1/3 x to the negative 2/3. All of this is over the denominator squared, which would be x to the 2/3, because when you do 1/3 squared, it's your 2/3.
Isn't it y to the negative 4/3? Oh, wait.
I changed my exponents right here, so mine isn't. If you don't change them, it will look differently. It'll simplify at the end, in the end to the same, but yeah, mine isn't. Okay, so there's one caveat to what's going on here. This problem is not solved in terms of x and y. Even when I simplify it from right now, it's also got a dy dx in it, doesn't it? But do you know what dy dx is? Sure you do. It's negative y to the 1/3 over x to the 1/3. So this will go in for the dy dx. We haven't done that before because we haven't done a second derivative before. So that piece of it makes this a little bit different. Let me put that in, simplify a few things going on here, and then I'll let you out here. So just copy these down for now. So you're going to have x to the 1/3. You have a 1/3 y to the negative 2/3 times negative y to the 1/3 over x to the 1/3. Then I have a plus because I have two negatives. Y to the 1/3, so I've got 1/3 y to the 1/3 and x to the negative 2/3 all over x to the 2/3. Are all my pieces in there okay? I know they're messy, but notice this x to the 1/3 and this x to the 1/3. One's the numerator, one's the denominator. These are going to cancel. That's friendly. You might also notice that there is a 1/3 in each of my terms right here. So I'm going to pull that 1/3 to the front for the moment and just write it in the front, just for simplicity. What does that leave me with? Well, I have y to the negative 2/3 and y to the 1/3, and it's negative. So there's a negative y. What is negative 2/3 plus 1/3? Negative 1/3. Very good. And then left over here on the other side, I have a y to the 1/3 and x to the negative 2/3. We're just about as cleaned up as we can get. The fact that we've got the negative exponents is not especially friendly. Let me just show you what it reduces to if you clean up and simplify the exponents. At the very end, without running through all the details, you end up getting the x to the 2/3 minus y to the 2/3 over, and there's a 3 from that 1/3 up here at front, and it's x to the 4/3. Okay. So I realize I've got a couple steps missing there at the end, but I know you guys need to get your next classes.